So the last thread that I mentioned in the list was the checkpointer thread, and this is the thread that just runs periodically. And when a certain amount of data has been written to the transaction log, the checkpointer thread starts up and does a checkpoint, and so by controlling the amount of data that's written into the transaction log, you can control the time that PBXT requires to recover. So it's a three-step process. In the first step, it flushes the index file. Now, I haven't mentioned anything about flushing indexes files up until now, and maybe you noticed that none of the index changes were actually written to the transaction log. This is actually an innovation that I think is only in PBXT. I've decoupled the flushing of the index from the actual writing of data. And that means what PBXT can do is it can actually recover index entries. On recovery, I'll speak a little bit more about that in a minute. It flushes the row index in the data handle file, and then it's done with flushing because the data log file was already flushed. It then notes the transaction log position and writes it to one of the restart files, and then it's done with a checkpoint. So what happens then on recovery? Now, the recovery process is not a background process, although it's got this great little thing here. It runs only on startup, and the recovery process is actually a very, very fast process because it's actually not doing any undo and any fancy stuff. All it does is it reads the restart file, or gets the most recent recovery point in the transaction log, and goes through it and does pretty much what the writer thread does. It just takes this and writes the record directly to the row index and the data handle files. And what it also does is it checks to see whether the index file has a reference to this record, and if it doesn't, then it adds one. So in that way, it also, if a record was rolled back, it will check that the index file, ensure that the index file doesn't have a reference to that record and remove it. So in that way, it recovers the index entries. And so the particular design innovations that are involved here, I've already been talking about the index entry recovery. What I didn't mention is this is the operation IDs. Now, if you are doing an update, you actually have to synchronize the update. You're updating of the cache. That's where I'm writing see if I can. Where I'm writing this, the cached, when I'm writing a record, I write the cached version of the row index in the handle data file. You've got to synchronize that operation with the operation that you're writing to the log, because the order of these operations is critical to the structure of the database. But the problem is, if I synchronize that, then I've got to lock both, and this could be a long time if for some reason some data is not in cache, then I've got to go to disk and read it, and I don't want to actually lock my log file for that time. So what I did was I created just a little ID which I increment, and every operation gets an ID, and they're allowed to go into the log in the wrong order, and the writer thread then has the additional responsibility of sorting them when they come out of the transaction log and then applying them in the correct order to the disk. So that's that. Update clustering is something I've still got to do. That just involves ensuring that updates, as I mentioned, no updates are ever done in place. So I'm always creating new records, and what I need to do is cluster those on a page basis. So that will make the writing of those eventually to the database much more efficient, because I can. It's more likely that they're actually going to be directly next to each other, and I can consolidate writes in that way. The update consolidation I also mentioned, and the ability for the writer thread to sort the updates in the background as they come out of the log before writing them to disk. So this design is quite flexible, and we look, as I said, we're going to look at two aspects of that, one related to solid-state drives, and the other related to what I see as the future of PBXT as a high availability storage engine. So I did some performance testing just using a simple C program and compared an SSD drive, an Entron SSD drive with the standard internal hard drive of 10,000 RPMs, I think. And I turned up two hotspots, the red block and the green block. This is the problem with SSD, incredibly slow random writing. If you compare, these are cache writes, it's actually writing into the cache, but the cache has been backed off to the disk all the time, and that's what's just putting a total drag on something here. I don't quite, it's extreme, because look at that. Yeah?
What's the size of the block?
I was using not 1 megabyte blocks, if that's what you're asking. I'm using 512K, 1K blocks.
512 bytes.
512 bytes, sorry, 1K blocks.
And what's your page size in your database?
32K, or 16K in the index, 32K in the data files.
So ideally you should probably look at that set, right?
Well, actually, I need to write the log file in much smaller blocks, you know, little transactions, and that's the critical thing. I do try to write it smaller if I can, so I don't want to write a whole 32K if I can just write a smaller piece. Yeah?
A couple suggestions. You might want to try, if you could try pre-allocating some section of a large chunk.
Pre-allocation makes a huge difference, and these were pre-allocated.
Oh, really?
Yeah.
Okay. The other thing is that I've seen in my benchmarks that changing the I/O scheduler.
Hi, Kevin.
Oh, yeah. Changing the I/O scheduler and some of those things can really improve the random rate performance.
Okay, so maybe you can give me some tips afterwards. Kevin says he's fiddling with the I/O scheduler to make that better. Okay, sounds good. Okay, but this is the basic problem anyway. This is the picture that I think everybody's seeing. You know, random writes are like really cool. This is from the disk, not cached. Cached obviously is pretty much identical for both. So this is the reason why you want to use SSD, and this is the problem that you basically have to solve. I think we can all agree on that. And then another interesting, this is supposed to be yellow. This is, I was surprised because this is the fastest thing that you can do, you know, on both drives, and that is a sequential write on an already pre-allocated, pre-cached file. So the basic idea behind the optimization is to maximize the sequential writes, minimize the random writes, and the architecture of PBXT actually makes this possible. So on the left-hand side we have a record structure optimized for hard drive, and on the right-hand side we have a record structure optimized for the SSD, where I've adjusted the size of the fixed length data in the record so that I'm writing mostly sequential here because the variable length data goes into the data log, and it's only written once, so that's another advantage. If you've got SSD, do it once because it's expensive otherwise. And hard drive prefers this configuration where you're doing less of this because this requires flushing twice. Once the data log and once the transaction log.